Okay, here we're going to work another equilibrium problem. But before we do, I just want to say, don't try to memorize the different ways that we can ask these equilibrium problems and then try to memorize the steps for each different type of question. Because there's essentially an infinite number of ways that we can ask these questions. And so we can always ask a question in a way that maybe you haven't quite seen before. And so if you just try to memorize steps, that's going to be a failing strategy. So what you want to do instead is just try to understand how equilibrium works, how to use ice tables, what the K and the Q tell you, and then when you're given the information on a problem, you can then try to figure out how to get to the information they want, rather than just trying to memorize steps. So let's take a look at this example. So we're told that we have an equilibrium mixture of N2O4 and NO2. But then we mess with the system and we change the volume. We cut the volume in half while keeping the pressure, or by keeping the temperature constant, right? And when we do that, that's going to change the pressures. And so our system is probably not going to be in equilibrium anymore. And so after we make that change to the volume and we mess with the pressures, the system will then move in whichever direction it needs to get back to equilibrium. Now, we've done that type of problem before. We have the initial pressures or concentrations, and if we know the equilibrium constant, we can calculate the equilibrium, in this case, partial pressures. Now, they didn't give us the equilibrium constant in this problem, but they did tell us that when we had these partial pressures, the system was at equilibrium. So we can use that to calculate K. So our equilibrium constant expression is going to be the pressure of NO2 squared divided by the pressure of N2O4. And so if we put in our numbers, we have 1.1 squared over 0.28. And so that gives us an equilibrium constant of 4.32. And I know that should only have 2 sig figs, but I want to keep some extra sig figs around to try to reduce the rounding errors as we go through this problem. Alright, now that we know the equilibrium constant, in principle we could go ahead and build the ice table, but let's do that on the next slide, because what we also need to do is we need to know what are our initial partial pressures. Right? These were the partial pressures when it was at equilibrium, but then when we changed the volume, we're going to change those partial pressures, and so we need to get what is going to be the new initial conditions for our ice table. So remember, the relationship between pressure and volume at constant temperature is P1V1 equals P2V2. And so we're looking for the new pressure. We're looking for P2. So if we solve for P2, that's going to be P1 V1 over V2. Now, we don't know what the exact volumes are, but we know that we cut the volume in half. So that means V1 is twice whatever V2 is. So our new pressure is going to be 2 times P1. So the new initial pressure of N2O4 Okay, so the new pressure of N2O4 is 0.56 atmospheres, and then the pressure of NO2, 2 times 1.1, so that'll be 2.2 atmospheres. All right, and so we have a little bit more room. Let's go ahead and set up the ice table on the next slide now that we know what our initial pressures are going to be. All right, so let's go ahead and build our ice table now that we know our initial partial pressures. All right, now for the change row, we don't necessarily know which direction the reaction is going to go. But we do know that K is 4.32, and we can use our initial concentrations to calculate Q. When we then compare Q to K, that'll tell us which direction the reaction goes, and so then we'll know whether to make which side of the reactants or the products negative or positive with the changes. So Q is, of course, the pressure of NO2 over the pressure of N2O4. So then we have 2.2 squared over 0.56, and that gives us 8.64. Right, so this is telling us that Q is greater than K. Right, and so I have too much NO2. Q is too big. So to correct that, the reaction is going to need to go to the left and convert some of the NO2 into the N2O4. Or, right, Pac-Man tells us the reaction is going to go to the left. So that means I'm going to lose product. And so let's call this minus 2x. That way x will come out to be a positive number. And so then this is plus x. All right. Now, if we hadn't done this analysis, and if we didn't know which direction the reaction was going to go, and we might have called this minus x and plus 2x, that's fine. All that's going to happen is x is going to come out to be a negative number. The way we've done it, x is going to come out to be a positive number, which is just a little bit easier to work with. So now that we have an expression for the equilibrium concentrations, and we know K, we can plug everything into the equilibrium constant expression. So we know K is going to be the pressure of NO2 squared over the pressure of N2O4. And so we have 4.32 is 2.2 minus 2x squared over 0.56 plus x. All right, so we need to move the denominator over here, get it out of the denominator, and so I'm going to multiply 4.32 times this whole thing, and that'll be my new left-hand side. So 4.32 times 0.56, I get 2.41, and then plus 4.32x. And then I'm going to go ahead and expand this numerator. So when I do that, I get 4.84 minus 8.8x plus 4x squared. All right, now we want to move everything to one side, so we want to set it equal to 0. And so I'm going to move these two over to this side. So I'm going to subtract negative 2.41 from 4.84, and I'm going to subtract 4.32 from negative 8.8. And so when I do that, I end up with 4x squared minus 13.12x plus 2.43 is equal to 0. And so now we're back to needing to solve the quadratic equation. So I encourage you to solve it however you would like. Pause it so that you make sure you get the same thing I do. Okay, if you've got your result, I plugged mine into Wolfram Alpha, and so I got two solutions as we would expect. And so I got x is 0.197 or x is 3.08. Now we know that only one of these should be reasonable. And I think the one that we are going to throw out is going to be this one. Right? Because if I look at the NO2 concentration at equilibrium, 2 times 3 is going to be 6. And so if I try to use this as my x, I'm going to get a negative pressure for the NO2. And we know that doesn't make sense. Can't have negative partial pressures. So that is the root that we're going to throw out. And so now we just have to use the x that we found that's going to be valid, combine those with these expressions, and we can get the equilibrium partial pressures of the NO2 and the N2O4. So the partial pressure of N2O4 at equilibrium is going to be 0.56 plus x, or that's 0.56 plus 0.197. And so that gives us a pressure of 0.76 atmospheres for the N2O4. And then for the NO2 at equilibrium, it's going to be 2.2 minus 2x. So that's going to be 2.2 minus 2 times 0.197. And so that gives us 1.8 atmospheres for the NO2. And so those are our equilibrium concentrations, or equilibrium partial pressures in this case.